But I just wanted to make sure everybody's okay with understanding p-values, type 1, type 2 errors, and significance levels. And I've seen on some of the assignments that there's some of them fell short, especially on the discussions in terms of understanding a basic hypothesis testing framework, what it is, what it's supposed to look like, and kind of symbol notation we use in each. There's some very simple yet very important heuristics that need to be followed. You can't just kind of willy-nilly do this stuff as you think is right, but it has to be done a certain way. So I can go over some of those heuristics with you. Since we did not have the first session last week, I do apologize. And I just checked the calendar. I think we are good till the 22nd. So I'm going to go ahead and also pencil this session in for the 18th of this month. So I'll be sending an announcement update for that soon, shortly. So while you're opening that up, let's go ahead and just kind of start with the basics. We have hypothesis testing framework that needs to be set up. When you're involved in hypothesis testing, you should always have a baseline statement. It's a statement of no effect. It means that there's no difference or no relationship that you observe. It's basically your status quo, and that is your null hypothesis. And I thought I was sharing my screen, but I'm not. So your null hypothesis, H naught, call that your null, is your baseline status quo. I didn't mean to divide it like that. Baseline or status quo statement of no effect or no relationship. Then you have your alternative hypothesis, H sub A or H sub alpha. Do that again. Which is basically a counter to what you said in the null. This is what you actually want to provide evidence for. It's a statement that there is an effect, that there is a difference, there is a relationship. And so in establishing these statements, you can come up with some examples, like for your null, you can say the mean of group A is equal to the mean of group B. And you can do it like this. Mean A is equal to, and see, notice I'm using the equal symbol here, to the mu of group B. So that's your null. Alternatively, you would say that the mean of group A is not equal to, if you're doing a two-tailed test, group B. Now, if you're doing a one-tailed test or left-tailed test, then you would go less than, a right-tailed test, greater than. But in all cases, we're only using symbols of not equality, inequality. Something like that. Those are the only symbols that you can use in the alternative hypothesis. In the null hypothesis, you can only use symbols like equals, less than or equal to, or greater than or equal to. Those are the rules. There are no two ways about it. It must be done this way. But you choose which symbol you want to use. These are just the available ones to use here. Let's make that larger. So far, so good? Okay, so when you're evaluating your hypothesis test, you have to choose a significance level. And that significance level is your alpha. And typically it's 0.05 or 0.01. Why? That's a great question. Why is it one or the other? Typically because, And I think some of you had the benefit of having me explain this to you in the previous course. You recall, maybe I did or maybe I didn't. Been a minute, but it all goes back to the normal distribution. And as it pertains to the normal distribution, we have this bell-shaped curve. There's some empirical rules associated with, you have the mean in the middle, your mu. As you begin to move out, as you begin to disperse the values, you have 68% plus or minus 68% of the data that's situated within plus or minus one standard deviation for the mean. You move out again, you have 95% of the data, which is situated within plus or minus two standard deviations from the mean. And lastly, you have your 99.7% of the data that's situated within plus or minus three standard deviations for the mean. That is your normal distribution, and it follows the 68, 95, 99.7% rule. Now, where does the significance level alpha come from? It comes from subtracting these values from 100%. So you take 99%, omit the 0.7. We were just not exactly accurate rounding, but it's 99% when it's subtracted from 100%, you have 0.01. So that's your significance level alpha of 0.01. And 0.05 when you subtract 95% from alpha, from 100%, you have your 5% alpha. So those are the two alphas that are used in hypothesis testing. The more common one would be the 0.05. It's always based on the 95% level. You'll see that in a lot of statistical software, especially Microsoft Excel. When you run a multiple linear regression, it has the 95% confidence level set up by default. And once you've chosen that significance level alpha, you'll have data. By then, hopefully you've collected enough data so that you can conduct your experiment. You need at least a minimum of 30 observations, because that's based upon the central limit theorem, which governs what we just looked at. The normal, in order for your data to approximate a normal distribution, you must have at least 30 observations. So I don't want to see any assignments or projects that have anything short of 30 observations. Otherwise, you're not conducting a proper test. So once your data is collected, you're going to go ahead and choose the appropriate statistical test. You pick the test that's most relevant for your experiment. There's no need to do something that's not part of your framework or what you're looking to test. So you just pick one experiment for this course. Not everything is applicable, like this chi-square test for association, which is meant for categorical variables. The classic test, what we just discussed, is the test for the mean, which is really straightforward and standard. All you have to do is pretty much select your data. You plug it in here in column B, copy paste it, and it's just one column. So if you garner a very large data set with a lot of columns and a lot of rows, you just pick the column that you're looking to set up the test for. And once you place your data in column B, notice how it's more than 30 observations. We have 50. You'll have all the relevant statistics placed for you here in green, which are already governed by these formulas. You don't have to do anything. All you have to do is copy paste into the blue section. Same thing here. Blue means that this is your value, your null, your alpha, again, 0.05. Standard error is calculated, and there's it follows the formula, which is your standard deviation divided by the square root of the sample size n. Now, what is the standard deviation? It's 28, and standard error is E7. We have number of observations, and E9 is, again, your standard deviation. Your test statistic takes the difference into account between the null and your mean, which is calculated from column B in the numerator, and it's divided by the standard error in the denominator. I can't tell you how many times I've seen folks just get this one wrong time and time again, even after I explain it. It is not any other value that you want it to be. It is not. It's if you're doing a test for batting averages in baseball, that is not your test statistic. Your test statistic is, again, the difference between these observed values and the mean in the numerator divided by the standard error in the denominator. And the standard error has its own very specific formula. So how you express that in part one is up to you, as long as it follows either the logic in this section, and it has to have either this answer, or you can show me the formula how it's derived, or a combination of both. But please don't make up any other kind of logic or reasoning for how you would calculate the test statistic. Let's make sure that we're on the same page when it comes to that. So for proportions, it's the difference in the proportions over the standard error, and chi-square test doesn't exactly have that, but just make sure that you have, again, see, they even give you the formula here, test statistic, the difference between the two means, and the null over the standard error. So that is a required section. You don't have to do much. You just have to plug it in, and this should match whatever you write in your project document. It would be a bit silly to have something completely different than what is in here, which I cannot match, and then have completely misleading results where you have something like this 0.998, and you say that you actually reject it, when clearly that's not the case. It even tells you that you need to fail to reject it. Why? Because it's greater than 0.05 or 0.01. It's greater than alpha. Whenever your p-value is greater than alpha, you whenever it's greater than 0.05 or 0.01, you must fail to reject the null hypothesis. Now, coming back to the basics, so I'll do a very quick review. The p-value is your probability that you're going to observe a value that in the data that's as extreme or even more extreme than what was actually observed, so that you're assuming that your null hypothesis is true. So you're calculating exactly how likely your observed result is under the assumption that there's no effect or difference. So back to what I was just saying, if your p-value is very low, less than 0.05, if that's your significance level, then that suggests that your observed data is unlikely under the null hypothesis. So you're basically edging very close and closer and closer and closer to considering rejecting that null hypothesis. Now, you can either reject your null hypothesis or fail to reject your null hypothesis. You can never accept. There's never such a thing as you can accept the null hypothesis, and never say the word accept. Similarly, you do not accept the alternative hypothesis. You simply, everything hinges on the null. You simply reject the null or fail to reject the null. That is it. Those are the only statements you make about your conclusions. Now, conversely, if your p-value is large, if it's greater than 0.05, then what you're saying is that the observed data is actually consistent with the null hypothesis, so you may not have enough evidence to reject it. And this is where we start getting into different kinds of errors, which is in part one. Type 1 errors, you're false positive. The easiest way to remember, it's a mnemonic device. Why is it a type 1 error? Well, because you have false and a positive. So false sounds like a negative word. It's not exactly, it doesn't carry with it up. Again, this is a mnemonic device. It's not backed by science. It's something to help you remember it. False is got a negative connotation. So sound wrong, false, right? And then you have positive, which is clearly positive. So there's only one of each. So it's a type 1 error. There's only one positive, right? Or one negative. So it's a type 1 error. A type 2 error is a false negative, because there's two words that carry a negative connotation to them. There's a false, and then there's a negative. There's two. So it's type 2. That's just how I remember it. Because if you just try to memorize this type of stuff without any kind of mnemonic devices, good luck. I don't know. It took me years until I figured this one out. But back to these errors. Type 1 is simply when you incorrectly reject your null hypothesis when it's actually true. So you fail to reject the null hypothesis when it's true, and you basically detect an effect that doesn't exist. And so that probability of making a type 1 error is your alpha. So again, type 1 error is your alpha. That's the probability. So if you set your alpha to 0.05, like we did over here, and in some of our experiments on the Excel sheet, you're basically saying that you're willing to accept a 5% chance of incorrectly rejecting the null hypothesis. And when it comes to type 2 errors, your false negatives, you're saying that you fail to reject the null hypothesis when the alternative hypothesis is actually true. So you conversely fail to detect an effect that does exist. So the probability, we don't cover this in this course, but the probability of making a type 2 error is your beta. And there's another way of measuring the power, which is 1 minus beta. That's the probability of correctly rejecting the null hypothesis, one that is false. So you don't need it for this course, but a low power means that there's a high risk of these type 2 errors. But all you really need to know for type 2 errors in this course is that you need to increase the sample size to help kind of offset these effects of these type 2 errors, to provide a larger data set size to potentially dampen some of those effects. That's basically it in a nutshell. And that's really all you have to do for this course. Just make sure you carefully select which test is relevant for your experiment, and kind of just depends on what your framework is, what you're looking to test, what you're what are you measuring. If there's 2 averages that you want to test, then you would use test for means. There's an independent test, there's a dependent test. It's really kind of on you to figure out which one is the more appropriate one here. But that's everything I wanted to share with you today. Is there anything you wanted to ask? All right then. So in that case, we'll just go ahead and end about 4 minutes early, and feel free to shoot me an email, and I'll do my best to reply within 24 to 48 hours. Guys, have a great weekend. Again, with respect to the hurricane and anything else that may present itself as an extenuating circumstance, do let me know. Don't be shy. Don't be afraid. I know if it's sensitive and something that you don't feel comfortable with being specific on, whatever the case is, just let me know whatever you're comfortable with sharing. There's a human element in all of this. We're all people, and life happens. What can you say? And take care. Have a wonderful weekend. I'll see you all next week.